the resurgent structure of not invariants on topological strings. So, Marcos, please.
Hi, hello everybody. Thanks a lot for the invitation to speak in this ReNewQuantum seminar. So I'm going to talk about the resurgent structure of quantum knot invariants and topological strings. So let me give a general introduction. The basic starting point for this talk and for the work of resurgence in general is perturbation theory in a small parameter. As you know very well, this remains one of the most fruitful approaches to quantum theories, still very useful, for example, in particle physics. But from our point of view, we are going to use the theory of resurgence. We have learned that the perturbative series encodes much more information than originally thought. And usually by an appropriate decoding of the perturbative series, of the standard perturbative series, one can find, for example, additional sectors of the path integral. And this is very useful in order to understand the different sectors of a theorem, but also involves very beautiful and challenging mathematics, in which actually one goes from the world of formal power series to the world of analytic complex functions and their underlying geometry. So this decoding that resurgence does is not only physically interesting, but it also poses a very interesting mathematical problem. So in what I will show in this talk is that in some cases, which I think is still not clear how often is this going to be the case, but in some cases, the perturbative series involves a hidden integrality structure. So it turns out that you can actually produce integers from perturbative invariants in a way which is slightly different from what has been done so far. And in many cases, these invariants can be interpreted as counting BPS states in a dual theory, a theory which is not necessarily the original theory. And two very interesting examples of such a situation are complex Chern-Simons theory and topological string theory. So my talk will be based on a paper I published a few weeks ago with Stavros Garoufalidis and Jie Gu, which is the case of complex Chern-Simons theory and knots in complex Chern-Simons theory. But I will also give an introduction to some work in progress with Jie Gu, in which we focus on topological strings. So I have to say that historically, this was slightly twisted because originally I started working with Jie on the case of topological strings, but then we realized that many things already in the context of complex Chern-Simons theory were not properly understood and not fully computed in previous work. So we switched to complex Chern-Simons theory, and then now we are trying to come back to topological strings. But as you will see, the formal structure of the two problems is very similar, which is already an interesting thing. Okay, so what is the starting point? Well, as usual in resurgence theory, our starting point is going to be the Borel method, which is a systematic and traditional way of making sense of factorially divergent formal power series. I think I have already presented this slide many times, but let's go through it for those of you who are not familiar, and also to fix some notation. So the starting point is a formal power series in a variable z, in a formal variable z. And we will assume that the coefficients of this series, an, are factorial, grow factorially. They go like n factorial. So in order to make sense of this formal power series, the first step is the Borel transform. So the Borel transform is a very simple thing. You just cut off the factorial growth by dividing every coefficient an by n factorial, and then you produce this auxiliary power series in zeta. Zeta is a different variable from z. So this is a new object. And this object is actually analytic at the origin. And this is, in a sense, the main object that we will use in this talk. Now, once you have this Borel transform, you can do a Laplace transform. And this Laplace transform.
What's your series now?
Is there any question there?
The teachings are not there.
Sorry, my microphone is not muted.
Could you please?
Can everyone turn off their microphone, please? except Marcos.
Thank you. So once you are given the Borel transform, you can do a Laplace transform, which is this integral formula here. And the result of this integral, when you can make sense of, when it's well defined, is a actual function of z whose analytical, whose asymptotic expansion is the original formal power series. So in principle, if you go through this triangle, you go through this circuit, you can actually produce an actual function starting from a formal power series. But my main tool here is going to be just the Borel transform. I'm not going to use Borel resummation, properly speaking, in this talk. Okay. So as I mentioned before, the Borel transform is analytic at the origin. Once you have this function, you can try to analytically continue to the full complex plane, and this is often doable in a systematic way. And this is what we call in resurgence endless continuable analytic functions. When you do that, you will find various singularities as you go through the whole complex plane. And I will call this plane often the Borel plane, and zeta is called sometimes the Borel variable. So when you do this analytic continuation to the complex plane, you will find many types of singularities, which can be poles, branch cuts, and so on. And this is the source of the richness of this resurgent approach, because each of these singularities, which in a sense are far from your original perturbative expansion is around the origin. Now, these additional singularities in the complex plane are going to be the sources of other functions. And this is the main point here. So the way you generate these functions is very easy. You just take this Borel transform and you expand it around each additional singularity, and this leads to new formal power series. Now, in this talk, I will restrict to a very simple type of functions, which are called resurgent functions, in which you only have logarithm singularities in this analytic continuation procedure. And this is enough for the purposes of the examples that I will be studying. So what happens? So imagine that you have a logarithmic singularities. This means that at a position zeta omega, this means that when you expand this Borel transform around the zeta omega point, you will have a logarithm, and multiplying this logarithm, you will have a formal power series, which turns out to be to have a finite radius of convergence, and you will have, in principle, a non-trivial constant in front of this formal power series. Now, this, if you go from this power series to if you do an inverse Borel transform, you will find another power series which is attached to this singularity zeta omega. So I will label the singularities by this index omega. So associated to this, each of these singularities labeled by omega, you will find another formal power series, which is going to be also factorially divergent. So you see that once you have the Borel transform, which is obtained by expanding around the origin, by looking at the other singularities, you will find additional formal power series. And this is the way in which, in resurgence, you actually explore new sectors of your theory by doing expansions around different singularities. And in many physical examples, these new functions that appear here, these new formal power series, correspond to physical sectors that could be, for example, expansions around different saddle points or your path integral and so on. Okay. So you start with a formal power series, you explore the singularities of the Borel transform, and you find other formal power series. But then with each of these new formal power series, you can repeat the procedure. Nobody stops you from doing this. So you can do again this procedure for all these formal power series. And by iterating this procedure many times, you will, sorry, I still hear kind of noises. Can everybody please mute themselves? Yeah, thank you. So when you do this procedure, you will generate a set of formal power series associated to a given theory. So this is what I just mentioned before. So you will get a set of formal power series, maybe an infinite set, and you will find also a matrix of Stokes constants associated to all these series. Remember that the Stokes constant appear in a sense the proportionality constant between one series and the other as you expand around different singular points. So the nth the end result of this is that the resurgent structure of a given theory will be given by a family of formal power series and a matrix of Stokes constants. And again, as I mentioned before, omega labels the different sectors. Now, if you are giving me a theory like this, like say QCD, or maybe QCD is very complicated, but even simpler theories, it's very hard to extract all this information. I mean, it's not an easy exercise, to put it mildly. And in particular, we know that the Stokes constants are often complicated numbers. So, for example, if you do this exercise for the different instanton sectors of pan level 1 or pan level 2, you will find a highly non-trivial transcendental numbers here for the Stokes constants. Now, in the examples that I'm going to consider, as you will see, this Stokes constant will turn out to be integers. Now, there are simple examples in which we understand why these integers are there. And these are the examples, for example, in which you have like a finite dimensional integral and you do expansions around saddle point with the stationary, with the method of stationary phases. And in this case, these integers are often interpreted in terms of intersection of integration paths. So there was a talk by Maxim Kontsevich in this series a couple of months ago where he was actually reviewing this. So there are some situations in which these numbers are integers, but these are typically situations in which there is a finite number of series. So there is a finite number of sectors and a finite number of Stokes constants. So my situation will be slightly more complicated. Very good. So let me give you a kind of very simple example in which this program of resurgence can be realized. This is not going to be my main example, of course, but I wanted just to mention it because it's actually a kind of sort of toy model for what comes. And this example is the exact WKB method. Now, in the exact WKB method, this series, this collection of formal power series can be identified very easily. They are just given by what are called quantum periods or Boros symbols. So how is this produced? So suppose that you have some Hamiltonian, some classical Hamiltonian in non-relativistic quantum mechanics, for example. So if you look at the points of equal energy in phase space, this defines a curve in phase space, which I'm going to call the WKB curve. Now the WKB curve is a complex curve, can be regarded as a complex curve, so it will have one cycle. So for example, you have a potential with this shape here, the one cycles are going to be associated to the intervals of allowed and forbidden motion. And the WKB method, if you want the Schrodinger equation, gives you an extension of the Liouville form to a quantum Liouville form, which is actually a formal power series in h bar square. And by integrating this formal power series in h bar square around the different one cycles here, you find a family of formal power series in h bar to the square, and these are called quantum periods. So the functions that appear in the WKB method, the functions phi of gamma associated to these cycles here are the functions that I was mentioning before in the most general case. So this is these quantum periods or these exponentiated quantum periods, which are called Boros symbols, are a concrete example of this resurgent construction that I was mentioning before. So in this case, it's quite well understood, and this is a finite set of Boros symbols. Now, the Stokes constants for this problem turn out to be integers, and they can be computed with the exact WKB method. So this was work done a long time ago in the early 80s and early 90s. And in this case, it turns out that the Stokes constant depends on the moduli of the curve. So they are not the same. As you change the shape of the curve, of the WKB curve, these numbers will jump, and this is the famous wall-crushing phenomenon. But the constants in different chambers are actually integers. So it's actually an interesting question. What is the interpretation of these integers? So is there any interpretation of these integers for a given curve? Now, it turns out that, as I was mentioning in the introduction, in some cases, you can reinterpret these integers in terms of natural integer numbers in some sort of dual theory. So in this case, this happens because of the following. So suppose that your WKB curve can be regarded as a Cyber-Witten curve for a supersymmetric theory. Now, it follows from work done by Gayotto-Muranitsky, which was inspired by Kontsevich and Soiberman. So it follows from this work that the Stokes constants in these theories compute BPS multiplicity. So this matrix of Stokes constants has a very simple expression. This is the intersection number of the two cycles, and then this multiplies the BPS counting associated to this homology class gamma. Okay, so this makes manifest that these Stokes constants are integers, and actually relates these Stokes constants to a counting of states, a counting of supersymmetric BPS states in a dual theory. So this is a very interesting interpretation, which in a sense makes manifest the integrality of these Stokes constants. And in a sense, what I'm going to uncover in this talk is a kind of much more complicated example of this situation. So I will show you how you can compute a matrix of integer numbers, a matrix of Stokes constants that are integer numbers, and they turn out to be related to BPS's counting in a dual theory. Okay. But this example of WKB is, of course, well understood, and everything essentially has been done already. Okay, so let me then come to kind of the main topic of my talk, which is complex Chern-Simons theory and the knot invariant associated to complex Chern-Simons theory. So the reason to look at complex Chern-Simons theory is because if you work from the point of view of resurgence, is because this is a very rich source of perturbative series, and on top of that you have a very beautiful mathematics associated to it. Okay, but we know that complex Chern-Simons theory is one of the places in which you might be able to follow this resurgent program to the very end. Okay, so I'm going to consider complex Chern-Simons theory on a 3-manifold M, but more precisely, I will restrict myself to the case in which M is the complement of a hyperbolic knot. And the reason is that in this case, one has a very simple model for the partition function of complex Chern-Simons theory in terms of a finite dimensional integral. So you can reduce the path integral of the complex Chern-Simons theory to a finite dimensional integral. So this is something that happens sometimes, especially in topological or supersymmetric theories. And in this case, this state integral it can be actually written down in a very explicit form. So this is work that goes back to Kashaev, Hikami, Dimofte, Gukov, Lennes, and Sagir, and it was put on very firm mathematical background by Andersen and Kashaev, who defined this theory in a completely rigorous way. So what comes out of this theory is that the partition function of complex Chern-Simons theory on a manifold, 3-manifold M, it's going to be a function of a coupling constant tau, which you can think about as an H bar. So this is a complex coupling constant in general. So it's defined over the whole complex plane minus the negative axis. And you just have to integrate some relatively simple function. And the building block for integrating this function is actually Fadeje's quantum Lie logarithm. So for those of you who know a little bit the subject, in this talk, I will actually focus on SL2Z. So the gauge group for the complex Chern-Simons will be SL2Z. There is presumably a generalization of this for SLNC, but I'm not going to look at that. So one of the nice things about this state integral is that the resurgent structure of finite dimensional integrals is relatively easy to understand. I mean, it's something that you can, in simple cases, has been completely understood, and this was also something that Maxime reviewed in his ReNewQuantum talk a few months ago. So in order to do the resurgent analysis of the state integral, you can try to follow this path, which is the standard saddle point analysis of a finite dimensional integral. So you just look at saddle points and you do the perturbative expansion around these saddle points. And since this state integral is related to complex Chern-Simons theory, it turns out that the saddle points of this state integral correspond to flat complex connections on this 3-manifold M. I'm going to denote these complex connections by sigma. And the expansion of this state integral around these connections has the following form. It has an exponential, which is inversely proportional to tau. So this is the standard classical action over H bar story. And then you have, so this is if you want the classical part. Here you have a complex number that I wrote it in here in general, which is associated to the complex connection sigma. And then multiply by this sort of classical factor, you will have all the quantum fluctuations which are encoded in this function phi sigma tau. So typically you will have a power of series in tau, which is also factorially divergent. That's usually are perturbative expansions in quantum field theory, and this actually happens here. This is the ANs for any given flat connections grow like n factorial. Now, given a three-manifold N, there can be many flat complex connections, but there are two special connections which are very interesting. One is the geometric connection, which corresponds to the geodesically complete hyperbolic metricon M. So I just want to mention that I will restrict myself to manifolds which are complements of hyperbolic knots. So there is always a geodesically complete hyperbolic metric on M. And you also have the conjugate. Since you are in a complex theory, you have the conjugate of this geometric connection. And in this case, the real part of this classical piece for these geometric and conjugate connections is plus or minus the hyperbolic volume of the knot. And this makes connection to the volume conjecture of Kashaev and so on. But the main message of this is that for these state integrals, you can actually work out in a very straightforward way these perturbative expansions, and very often you can calculate these numbers at a very high order in the loop expansion. Very good. So if you now do the resurgent story, you will find that the saddle points lead to singularities in the Borel plane, which is the standard thing that I was mentioning before. This is a generic thing that happens in resurgence theory. So in order to be concrete, let me actually focus on a very particular example, which is the complement of the figure A knot. This is in a sense the simplest non-trivial example of this story. So in the case of the figure A knot, you have only these geometric and conjugate connections in the path integral, in the state integral. And this power series associated to this geometric connection can be actually worked out up to very high order. So I just showing you here some of these numbers. And this is actually interesting because the expansion around the geometric connection is actually the expansion of the Kashaev invariant to all orders. And if you look at the Borel plane of this power series, you will find that there is a singularity here, which is exactly located at V, which is the hyperbolic volume divided by pi. Now, there is the conjugate connection, which in this case is related in a very simple way to geometric connection. It's just switching the sign of tau. And if you look at the Borel plane of phi z of tau, you will also see a singularity of minus v over pi. Okay. So if you just look at this, singularities, this looks very much like what you would find in a standard finite dimensional integral. So it looks like a very simple situation. Now, fortunately or unfortunately, the situation is a little bit more complex than that. So these singularities in the Borel plane are actually, as I mentioned before, they are classical in the sense that this singularity means that this series is seeing this series, and this singularity means that this series is seeing the other series. So you have two series, and each of them has a singularity which refers to the other one. Okay, so this is in a sense a very standard situation in resurgence for finite dimensional integrals, but and as I mentioned here, this can be analyzed in some detail. The Stokes constants can be computed. There is just essentially two Stokes constants here for these classical singularities. But in Chern-Simons theory, and in these state integrals, we have an additional complexity, which is very typical of these examples, which is the fact that there is a multivalueness story here. And this is because the Chern-Simons action is only defined up to 2 pi I times n. And this is reflected in the state integral in the fact that the function that appears in the potential is not a holomorphic function in the complex plane, but is a dilogarithm. And this also has multivariance properties. So when you do that, when you take into account that, one realizes that in the Borel plane there is actually not only two singularities in the two different Borel planes, but on top of each of these singularities there is an infinite power of additional singularities due to this multivalence. And from the point of view of the action, this is very simple to understand. The classical Chern-Simons theory, Chern-Simons action is defined up to 2 pi I times an integer. So it means that on top of these classical actions that you find here, you will also have these additional singularities here, which are in vertical lines over this previous action, over the classical action. So in the case of the figure A naught, V was plus or minus the hyperbolic volume. This imaginary part is 0. So you will have the actual picture of singularities here is much more complicated. You will have a tower of singularities on this non-trivial singularity here, and in addition, you also have a tower of singularities over 0. So this is the general structure of singularities you have. So you have the classical story, the one that you would find in a standard finite dimensional integral, and on top of that you have these towers, which are singularities of the Borel transform. And this you can see numerically, for example, very clearly. And this is as it should be because of this multivariance phenomenon. Let me mention that these towers of singularities on top of sort of classical singularities appear very often in many examples. Every time you have some sort of multivariance structure, you will have something like this. And one of the cases in which you have this multivariance structure is in topological string theory on non-compact Calabi-Yau manifolds. This is related to the fact that the natural variables in mirror symmetry for toric Calabi-Yaus are exponentials of and then this is going to give again a multivariance structure. I will mention this at the end of this in the second part of the talk. But this turns out to be a generic phenomenon. Let me point out that in the case of topological string theory, I think the first paper where this was pointed out very clearly was in a paper by Pasquetti and Schiappa, and it has been studied. It has been pointed out in many other examples in topological string theory. So already you can see here that complex Chern-Simons theory and topological string theory share this structure of towers of singularities. Very good. So what does it mean from the point of view of physics? Remember that singularities in the Borel plane correspond to non-perturbative sectors. So it's actually very easy to see that from the point of view of non-perturbative sectors, these towers correspond to non-perturbative corrections which are of order q twiddle to the n. So here q twiddle is the exponential of essentially -1 over tau. And this gives me a scale for non-perturbative effects in this theory associated to these towers of singularities. And let me also mention that generically, these effects are very, very, very small. And so if you really want to see these effects, this means that you have to really control your theory with a huge precision. And this is one of the difficulties in actually controlling these singularities. They really correspond to very tiny non-perturbative corrections. And this was a problem to compute them until recently. So if you have an infinite number of singularities, this means that you will have an infinite number of sectors. So we are going to label the different sectors of the theory by a pair, including this pair is it has a flat connection, which if you want labels the classical structure of the theory, and then you will have an integer n, which takes into account which additional multivalueness you are taking into account. Okay, you are looking at. Now, since sectors are labeled by a flat connection and an integer, the Stokes constants will be labeled in principle by a pair of flat connections and a pair of integers. So, and here maybe if you look at this type of problem, you might think that these towers of singularities are somewhat trivial because they come from multivalueness. So one could think that, essentially all these singularities will give you, say, copies of the basic singularity. So for example, if you go here, you could think that all these additional singularities are just copies of this singularity and of the origin of the, well, this is not really a singularity, the origin of the Borel plane, but you could think that these things are essentially very simple or even trivial. In a sense, they are not very difficult, and one of the reasons, one of the aspects in which they are not very difficult is that the trans series, the different formal power series that they obtain, can be obtained by a simple multiplicative rule. So you have a sector phi labeled by sigma and n. It turns out that this general series is going to be a product of the classical asymptotic expansion phi of sigma, and the one that you would obtain by doing a standard saddle point analysis of this integral, times this factor q to the power n. So from the point of view of this formal power series, the structure is very simple. In a sense, you can see that these additional singularities do not change the expansion itself. They just change the classical part of the expansion, but the classical part of the trans series, but they don't change the perturbative coefficients. So in that sense, this looks like very simple, but it turns out that the Stokes numbers are actually non-trivial. In spite of this factorization property, the Stokes constants themselves are highly non-trivial. Let me first point out that due to this multiplicative property of the trans series, the Stokes constants can be shifted. So you can just put one of these integers to 0 and the other to n. So the Stokes constants actually depend on two flat connections and a single integer n because of this sort of translation invariance property. Now, we were very surprised to find that if you do an explicit calculation, as I said, you need a lot of precision to do this calculation, you find that these Stokes constants are highly non-trivial integer invariants of the node, a highly non-trivial collection of integers. Since we are extracting this from a topological invariant of the node, these are integer invariants of the node. So explicit calculation, for example, for the figure 8 node, remember that this you can actually associate this Stokes constant to a pair of connections and to an n. So this means that if I look to the Borel plane of this series, which is the series G, I will have these numbers here, which are non-zero. So these are the Stokes constants corresponding to sigma equal to sigma prime equal to G, and then the different n's here, label this n here. And these numbers here are the Stokes constant associated to sigma equal to G and sigma prime equal to C, which is the other sector of the theory. And you have all these towers. And the same thing happens for the other sector here. Okay, so these numbers here are labeling these numbers that I introduced here. And I only put the upper half plane because you can see by using symmetry arguments, you can see that the lower half plane, the singularities in the lower half plane are going to be related to these ones. Okay.
Oh, excuse me, Marcus, before
Yes.
I lost in numbers. So your points, they correspond indeed just to multivalueness, to the universal cover of,
yes.
Okay. And these S, they're just what numbers of gradient lines between these critical points of the function of the universal cover.
I guess they can be interpreted in that way. I don't know if this is a kind of, right now, this doesn't give me a clear way of doing this calculation, precisely because of this multivalueness property, which makes things a little bit more obscure to me. But I would say that they could be interpreted in this way. But yes.
Maybe I can add that would mean that then they are sort of SL2C instanton counts.
Yes, they are. In a sense. Well, they count the intersection number between these, these symbols. But once you lift them to the multivalueness, so I don't know if they can be interpreted as instantons.
No, I think, sorry, I think it's really, you consider product of manifolds with R and consider instantons with two boundary conditions. Yeah, that's it.
Yeah, like in this Witten story, yeah. So
Okay,
then integrality should be sort of understandable. Because
yeah. From that point of view, yeah, if you have a formulation in terms of that, then the integrality should be manifest. But I think I don't think this is. I'm not sure how practical is this point of view in order to actually determine this integer. So that's another issue. So let me actually.
We can continue discussing back afterwards.
Yeah. Sure. So let me tell you how to at least characterize these integers, because we did some calculations, but we have a conjectural characterization of them, which I think is quite solid. So let me tell you how you would go about this. Now, the first thing in order to show this characterization is the following. If you have seen at these numbers long enough, you will realize that the column, this first column here, is a number that these numbers have been computed before, and surprisingly, they have a clear interpretation as a count of BPS states in a dual theory. So this is what is sometimes called the Dimofte-Gayotto-Gukov index, and it comes as follows. It turns out that complex Chern-Simons theory on three manifolds have dual supersymmetric conformal field theories in 3 dimensions. And in this superconformal field theory in 3 dimensions, you can count BPS states, and there is a particular sector in which you can count these BPS states, which is the sector of magnetic zero number. And when you do this calculation of this index, you will find exactly these numbers here. But notice that, of course, these descriptions are very different. Here I'm doing a calculation of Stokes constants in this complex Chern-Simons theory, and here I'm counting BPS states in this dual theory. But this is, in a sense, I was expecting something like this, because we know that the integrality of these Stokes constants very often is related to some counting of BPS states, and that's why I showed you before the WKB example, which is in a sense a toy model of this. Now, if you want to have a more precise description of all these integers, what you have to do, well, I mean, we found that the way of having a description of this, inspired by this observation, is to look at an auxiliary description of the state integral, which is called the block or the holomorphic block decomposition. So in the case of simple hyperbolic knots, this was worked out by Garoufalidis and Kashaev, and in particular by Garoufalidis and Saguier, and this was the key thing to actually characterize these integers. So, one way of collecting these numbers in a good way is to introduce a matrix of Stokes Q series. So remember that the Stokes numbers are labeled by a single n and then 2 flat connections. So you can construct a Q series out of this Stokes constants, one series for the positive and the other series for the negative, and this will give you plus 2 pairs of matrices S and S prime whose entries are actually Q series. And it turns out that these Q series are actually related to, can be actually computed as bilinear expressions in fundamental solutions of a very simple linear codifference equation. And in the case of the figure 8 knot, which is the example in which I will focus now here, this linear Q-difference equation is very simple. It's just this equation here. And it turns out that all these numbers are conjecturally given by bilinear expressions in solutions of this equation. Okay. So that's our main conjecture. Just to make sure that you see that we have really explicit formulae, all these numbers that I showed you that we were computing like one by one can be actually generated by a family of Q series, which are very explicit. Those of you who do calculations for this figure 8 knot will recognize some of these formulae. And this matrix, for example, the S plus matrix, is just a bilinear expression in the series G plus small g plus minus and capital G plus minus, which I have written here. I just want to just show you this just to make sure that you know that we have a very explicit description. And we have also obtained similar explicit results for the figure 5.2 for the 5.2 knot, for the next non-trivial hyperbolic knot. So this knot is much more complicated. The expressions are a little bit more complicated, but you can also give a complete description. So the picture that emerges from this is the following. Now, first of all, for any hyperbolic knot, we conjecture that the Q series associated to the geometric representation, it's always given by this DGG index, okay? You have to subtract -1 for convention, but these Q numbers, these numbers that appear in the Q series are just the DGG index. So this is one particular entry of this matrix. Now, in general, all the entries of these matrices are actually bilinear expressions in solutions to a linear difference equation. And this linear difference equation, you can actually read it from this holomorphic block decomposition of the state integral. And I would like to mention that similar results for this Stokes constants associated to these multi-covering properties were recently announced by Konsevich. Now, there is a kind of simpler case of this Stokes Q series, which is related to compact Chern-Simons theory, to SU2 Chern-Simons theory. So in some cipher spaces, it's very easy to calculate these Chern-Simons invariants. And in this case, you can actually see essentially from first principles that you can compute this Stokes Q series, which in those cases, these Stokes Q series are related to mock modular forms. So this was like first point out, I guess, by Kostin and Garoufalidis, and then by myself, Sergei Gukov, and Pavel Putrov in our paper on resurgence in Chern-Simons theory. But this is, in a sense, like a simpler type of example. So this is the picture that we find. These are the kind of general conjectures that we expect, but we have not really proved these conjectures. Okay, so maybe this is a good moment to ask questions before I mention the case of go into topological strings, which is, I will be shorter in the case of topological strings, but if there are any questions about the case of knot.
I have kind of a bit confused. You have this Q, which is related to tau, I assume that exponent 2 pi I tau,
Yes.
and you have this Q dual.
Yes, yes.
Somehow I confused because
no, I know
that everything is classical.
No, but let me mention, the physical variable is this Q twiddle, but here Q is just a formal variable. Okay, here just Q is just a way of encoding all this information. So here Q is a formal variable, but the physical variable, if you want, should be Q twiddle. I mean, this is just to have like a formal encoding of all these numbers. After all, what we want to compute are these numbers. So this is just a formal way of doing it.
Okay.
Okay. So what is surprising in a sense is that very similar structures appear in a different theory, which is topological string theory and toric Calabi-Yau manifolds. So let me sketch this story because this is still work in progress. I don't have a complete picture, but let me sketch how this goes. So let's suppose that you have a toric Calabi-Yau X, and then you compute the partition function of this topological string theory, but not the standard Gromov-Witten theory, but the topological string partition function in what is called the conical frame. That's not what people do in Gromov-Witten theory, as I mentioned, but is related to this Gromov-Witten theory by just a symplectic transformation. Now, this partition function depends on two variables. One is the string coupling constant, and the other is the Keller parameter lambda. Here, for simplicity, and assuming that you have only one single Keller parameter in the game, you can have Calabi-Yaus with a higher number of Keller parameters, but just for simplifying my life, I'm going to suppose that there is one single Keller parameter. Okay, so this is a formal power series in tau whose coefficients depends on lambda, but each FG of lambda is a formal power, can be written as a formal power series around lambda equals 0. Okay, and this is what makes the conical frame very, very, very special. Okay, Now I'm going to define an infinite family of formal power series. And to do that, I will quantize the Keller parameter. I'm going to take lambda equal to n, where n is a positive integer, times tau. And if you do that, you will find an infinite family of formal power series in tau times an exponential. So this is very much like the kind of power series that are obtained in complex-Simons theory. And this is just information that you can obtain from perturbative topological string theory. Now, why I'm doing all this? I mean, it's not completely natural, right? I mean, for example, this quantization of the Keller parameter, it's sort of related to kind of ADS-CFT correspondence, or, but it's not clear why I should do this. Now, there is a very clear motivation for doing this, and this is what we call the topological string spectral theory correspondence that was developed by Alba Grassi, Yasuyuki Asuda, and myself some time ago. And this correspondence has many implications, but one of these implications is that these power series, Zn of tau, are actually asymptotic expansions of spectral traces of trace class operators. So there are some, given any Toricala-Villan manifold, X, you can construct a trace class operator such that spectral traces of this operator, and these are called fermionic spectral traces because you have to take some anti-symmetric product of your Hilbert space L2R. These spectral traces have an asymptotic expansion which is given by this series. And n here, it's related to the power, to the dimension of the Hilbert space, if you want, or more, well, to the number of powers of the Hilbert space that you are considering. Okay. Now, so that's the motivation. But these formal power series are given to you once you know topological string theory. Topological string theory gives you all these power series.
Can I ask some question?
Yes.
So in this equation, which side can you compute?
In which this equation? Both.
Yes. I see. So why is it a conjecture?
Because I have not proved it at all orders.
I see.
So yeah, the way we have tested this is we have computed this up to a given order in powers of tau, and this you can also compute it up to a given order in powers of tau. So we have tested this up to 300, order 300 or so, but I don't have like a first principle proof. I mean, in some particular Calabi-Yau manifolds, you get very close to a proof. So you can find some limiting cases in which this is very much almost proved, but still we cannot. I mean, we don't have a general proof. And again, the computations are example by example. So this is why it's still a conjecture.
And this Zn, you said it was not what the Gromov-Witten theorists compute, but related to it somehow.
Yes. Yeah. This is. You see, when you work in the B model, if you want, you can essentially expand these topological string free energies around any given point in model space. So you have to do some sort of chase of symplectic frame in order to go to the special points that you want. So in principle, you can compute all of the topological string partition functions around any of the kind of singular points in model space. One point is large radius. This would give you the standard Gromov-Witten. The other is the orbifold point. Typically, when you have an orbifold point, this would give you orbifold Gromov-Witten invariance. But in a sense, the most mysterious point is the conifold, because the expansion is very well defined formally, but there is no a priori geometric interpretation of the quantity that you get in this expansion. But in principle, you can do that.
Oh, just some question. Is this can be this capital N interpreted to have some UN series somewhere?
Yes, absolutely, absolutely. Yeah. It can be interpreted. You see already. You can interpret this fermionic spectral trace as some sort of UN matrix integral. So that's the UN that is coming into the game. Okay, now this is a kind of complicated story, but let me give you an example. Well, the first question you could ask is the following. Now we have a family of formal power series in the string coupling constant, so it would be interesting to understand the resurgent structure of this series. I mean, this presumably should tell you something about the non-perturbative structure of string theory, because see, in gauge theory, even complex-Simons theory is relatively well understood. I mean, all the saddle points are related to complex flat connections. I mean, this is the world of gauge theory. I mean, we sort of are familiar with that. But in the case of string theory, it's not clear what are all these, it's more complicated what are all these, non-perturbative sectors. So doing resurgent analysis of this perturbative series is a way to kind of understand non-perturbative sectors in string theory. So I'm going to kind of give you some information about one particular example. This is an example which is very rich, but can be worked out in detail. And this is what is called local P1 times P1. So this is the anti-canonical bundle over P1 times P1. So it has like described by a Newton polytope of this form. And the operator that is associated to this local Calabi-Yau can be essentially read from the Newton polytope by assigning to this axis the Heisenberg operator X, to this axis the Heisenberg operator Y, so that X and Y are canonically conjugate Heisenberg operators on the real line, so they commute to IH bar. And then each vertex of this polytope gives you a term here, so you get e to the x plus e to the minus x plus e to the I plus e to the minus y. So these are the 4 vertexes of this polytope. And this is not rho, because this operator is manifestly not trace class, but the inverse of this operator is trace class for H bar real and positive. And this is the trace class operator that we want to look at. Now, it turns out that the string coupling constant is not really H bar, but is more like 1 over H bar. So we are going to study the trace of this operator in the regime in which H bar is very large, which corresponds to the regime in which tau is very small. So the spectral theory of this operator can be actually understood in this limit of H bar very large, and you actually can produce such an expansion. So this would be the case n equal 1 of what I was showing you before. And then what happens when you do this? Well, as I told you, you will get an exponent times a formal power series in tau. So the exponent involves G here is the Catalan number, and then you have like a power series, very much like the power series that you find in complex Simon series, a power series in tau. So I'm going to call this power series phi of G of tau. So this is just a name. We don't know if this corresponds to some sort of geometric connection in a 3 manifold. But what is interesting is that the exponent appearing here, the number appearing here, it has a geometric meaning. So it turns out to be the volume of the Calabi-Yau at the conifold point. So what does it mean? I mean, of course, this is a non-compact Calabi-Yau, but the Keller parameters can be evaluated at different points of moduli space, and they are giving you, in a sense, the volume of the Calabi-Yau. And in a sense, the smaller volume that you can have in a Calabi-Yau is the evaluation of the Keller parameter at the conifold point. That's a very non-trivial number. It's actually typically a transcendental number. And in the case of local P1 times P1, the volume of this Calabi-Yau at the conifold point turns out to be proportional to the Catalan number. So this quantity that appears here, it's a classical geometric property of the Calabi-Yau. And actually, this turns out to be very general. And this is what I like to call the volume conjecture for toric Calabi-Yau manifolds. It tells that the trace of these trace class operators in this limit in which H bar is very large goes like the exponential of the volume of the Calabi-Yau. So,
sorry, Marcus. Yes. What is the volume of non-compact Calabi-Yau?
Is the value of the Keller parameter evaluated at the conifold point. My definition.
Okay. There is 5 minutes left.
Yes, I know.
Yeah.
But so this is what I mean by volume. Okay, it's a natural definition of volume in a sense, and this is what you find here. But what is interesting about this conjecture is that you have a kind of quantum object here associated to the quantization of the Calabi-Yau manifold, of the mirror curve of the Calabi-Yau manifold, and it turns out that this trace, this quantum object, is asymptotically related to a classical geometric property of the Calabi-Yau. And this is why I call it the volume conjecture, because in a sense it's like this volume conjecture of Kashaev, that something very quantum, which is the Kashaev invariant or the Jones polynomial, has an asymptotic control by some sort of classical geometric quantity, which is the hyperbolic volume. So this is, in a sense, the analog of this. Now, here it turns out that for this local Calabi-Yau, you can now take this function phi of tau. This is the only thing that the string theory, topological string theory gives you. This is the only formal power series that it gives you for n equal 1. But then you can study the resurgent properties of this series and do this game that I was telling you before. Just look at the singularities in the complex plane, span around them, and try to see what you get. And what you get is exactly similar to what we got in the figure 8 node. First of all, we find that there is another formal power series involving this resurgent structure, which is obtained from this series just by switching the sign of tau. Okay, so there are two sectors, but this sector here, I mean this other sector, this complex conjugate connection, from the point of view of topological string theory, is already a little bit mysterious, because in topological string theory we just have one sector, which is what Gromov-Witten theory gives you. Okay, and its symplectic transformations. So now it turns out, in addition, that there are also additional towers of singularities. This time they are not located at 2 pi n, but at pi n. And you can also compute these Stokes constants numerically. So I'm just showing you some results that we were obtained in the last few weeks. And this is, again, part of the structure of topological string theory. But in this case, we still don't know what is the physical or mathematical interpretation of these integers. But they are part of the topological string package. I mean, once you define Gromov-Witten theory in a toric Calabi-Yau manifold, these integer numbers are there, are part of the structure. So we hope that we will be able to understand a little bit better these integers. Maybe they are related, again, to some sort of BPS counting. And of course, this is not the first time resurgence is studied in topological string theory. But having other approaches, in particular, Ricardo Couso, Ricardo Schiappa, and collaborators have actually worked out very beautiful resurgent structures by using the holomorphic anomaly equation. So one of the things that we would like also to understand is how this is related to what they did. But I mean, the message here is that topological string theory on non-compact on toric Calabi-Yau manifolds is formally very similar to what is obtained in complex Chern-Simons theory once you look at the right quantities. Okay, and I just want to mention, just to finish my talk before the conclusions, I have 2 minutes, that what makes this formal similarity very concrete is that when you actually compute the kernel, the integral kernel of this operator, you find that it's built up of quantum dilogarithms and Faddeev's quantum dilogarithms. So this is, in a sense, kind of the formal thing that is underlying this this similarity. But again, you know, we still don't have like a kind of complete picture for a topological string as we have for the case of hyperbolic knots. This is still work in progress. Okay, so let me come to the conclusions. So one general message is that perturbative series have a lot of information encoded in it. And part of this information in these cases is actually an infinite number of integer invariants. So in particular, you have like an invariant for knots based on perturbative series. You will be able to extract integer invariants. And this is a different route to integrality. It's a little bit different from the previous ones. For example, a nice approach to integrality, which was pioneered by Saguier and Ruth Lawrence, has been developed in particular by Sergei Gubkov and collaborators, is to repackage the perturbative series as a radial asymptotic of a Q series. This also gives you integer invariance, but it's different from what I'm proposing here. Here I'm proposing to look at the Stokes constants. So maybe you know, there are some relationships between these two approaches, but a priori they are different. In principle, the Stokes constant approach, you can always do it, essentially. What is not guaranteed is that you're going to get integers. Now, in the case of complex Chern-Simons theory, we have been able to understand, at least conjecturally, this resurgent structure in the case of complements of hyperbolic knots. And what we see is a relationship between the Stokes constants, which are integers, and then this BPS counting in this dual 3D theory. And the same structures turn out to appear in topological string theory, but we are not we are not even, I mean, here already the classical sectors are not completely clear. I mean, in the case of complex Chern-Simons theory, the classical sectors are just complex flat connections. But in the case of Chern-Simons theory, we don't even know why there are what these additional sectors are. I mean, here in the example I showed you, it looks like these two sectors are very similar, but in general, you know, we don't know what additional sectors in string theory are giving you all these series. Okay? And there are many open questions. One very obvious one is what happens in the case of hyperbolic nodes. What happens when you deform the hyperbolic structure? I mean, all this story I told you has a one parameter deformation, and in principle, this one parameter deformation should make contact with the A polynomial and the AG conjecture and so on. In particular, we expect that these linear Q-difference equations are going to be related to the AG conjecture for hyperbolic nodes. Now, another question is if one can actually obtain these Stokes invariants by doing some sort of WKB analysis. But maybe one speculative idea is that you take the curve defined by the A polynomial and some sort of WKB analysis of this curve will give you another way of computing these Stokes constants. Another interesting question is that you know, as Maxime emphasized also in his talk a couple of months ago, one can, once you have all this package of resurgence, you can reformulate the problem of computing the original invariance as a Riemann-Hilbert problem for this resurgent structure. So in principle, we could now use the Stokes constants to compute the state integral invariants themselves through a Riemann-Hilbert problem. And working out this would be very interesting. And well, of course, we should try to prove our conjectures or justify them physically already. I think that would be very interesting. And all this is very clear for complex Chern-Simons, but for topological strings, much more work is needed because the underlying physics is much more complicated. But I think this is a very interesting direction to understand better topological string theory. Thank you very much for your attention.
Thank you, Marcos. So we'll take a few questions. So first, Maxime.
Okay, yeah. No, I just got a bit lost at the very end. When you speak about topological strings, you have formal power series depending on integer parameter n, yeah?
Yes.
Capital N. So yes. You get infinitely many kind of...
Absolutely.
If you wrote just for n equal 1, something like this, yeah?
Yes, yes, yes.
I see. So you get kind of not one
absolutely.
Depending on parameter.
This is in a sense like doing SLNC in the case of complex Chern-Simons theory, you see. So here I'm doing just SL1C or SL2C. So this is the trivial case. Yeah. But in principle, one can do this resurgent analysis for all these M's. Mm-hmm. So in a sense, it plays the role of the rank of some gauge group, which we don't.
Yeah, because then one should have also some resurgent property in capital N as well. Yeah, for this.
Yeah, absolutely. And this is what people actually did before. What people tried was to look at the resurgent properties as a function of tau. For this series themselves, okay? So they kept lambda fixed and they were looking at this series as functions of lambda. So you would have like a parameter-dependent resurgence. But what I'm proposing here is slightly different. This is very natural from the point of view of ADS-CFT because what you're saying is that this scalar parameter is n times the coupling constant, and then instead of thinking, if you want, this is like thinking about the Toft expansion, and this is like thinking in kind of perturbation theory. So in a sense, what I'm doing here is to put the different n's equal to 1, 2, 3, or 4 in order to see the resurgent properties from the point of view of pure perturbation theory. Okay, so that would be like studying the gauge theory in a standard perturbation theory instead of studying it in the Toft expansion.
Well, we have other questions. Please, everyone, can you write a message in the conversation if you want to have a question? So Jürgen has a question.
Yeah, so I just wanted to try to go back to somewhat the beginning, Marcus. So two questions. the first one, where you look at the initial expansion in Chern-Simons theory, where you called it phi g or something like this, do you actually start with SU2 quantum Chern-Simons to get this expansion, or are you expanding the integral that Renat and I have in that case?
Yeah. So here I take the integral for SL2C and I just expand it. Okay. So this is SL2C Anderson-Kasayev invariant, if you want, and I'm doing just the expansion, the perturbative expansion. Okay.
Okay. So it is this complex theory and not the SU2 thing, not the color Jones.
No. This is really the complex theory. This is So this is, for example, here for the figure right now, this is what you would get from the geometric connection, and this is the Kasayev invariant. So this is really the standard complement of a knot.
Yeah, because you see, I mean, what I would call the Kasayev invariant, Kasayev can correct me because he's here as well, but that would be the color-Jones polynomial evaluated, correlate the root of unity and the color.
Yes.
And Renat and I have been battling a lot trying to prove that invariant is specifically related to the state integral, and that's why I'm asking the question.
Absolutely, this is non-trivial at all. I mean, the relation you are pointing out is I don't know how to prove it. It's just a kind of fact of life that if you do the expansion of the geometric connection in your state integral, you will find the expansion that you find there is the same that the all order expansion of the Kasayev invariant. So in particular, the Stokes constant that I'm computing should be the same ones that you would find for the Kasayev invariant. So take the Kasayev invariant, just define in the standard way with the Jones polynomial, and then just do the power series expansion. You will get a formal power series, and now you do resurgence on this formal power series. Since everything I have done is at the level of purely perturbative properties of this formal power series, you would get exactly this construction.
Okay. And then, super. And the other question was, so you have this 2x2 matrix, when you go on to discuss the block decomposition and the Stokes, I mean, if you go a little further in the slides, I think the next slide or next, there we go. Yes, so there's this 2x2 matrix here. So is there any role of the trivial flat connection in this picture and the 3x3 picture somehow, or?
No, I think no.
You have the hyperbolic and the conjugate, but what about the trivial flat connection, which clearly is there?
Yeah, absolutely. I mean, as you know, the state integral is not sensitive to this trivial flat connection. So for the trivial flat connection, we should do a different analysis. Yeah, and this is not seen at that level. Okay, it would be very interesting to add this into the game. But but we don't have anything special to say about that. This would be a different story.
Okay. Thanks.
There is a question by Vivek.
Yes. Vivek,
you can ask your question.
Yes. Hello. So you have presented this as two stories, one in the case of this complex Chern-Simons and one for topological string. As you used to tell us very frequently, at least some kinds of Chern-Simons invariants have interpretations as topological string.
Yes.
Can you, in fact, cast the first story in the language of the second? Is there an...
unfortunately, I have not been able to do that, and this is very frustrating. So for the topological string theory, what happens is the following: you have this spectral theory interpretation, so in terms of these operators and so on. But what is surprising is that, and for this I don't have a deep reason, is that when you really work out the details of this spectral theory story, you find that the formal structure is identical. It's very similar, not identical. It's very similar to the one of complex Chern-Simons. But there are also important differences that I have not emphasized. And for example, one difference which is important is that in complex Chern-Simons theory, essentially, you have some sort of symmetry between B and 1 over B, just because the quantum dilogarithm has this symmetry. So when you change tau over 1 over tau, you have more or less the same theory. While in topological string theory, this is not the case. There are two different sectors, and this means that the expansion when around tau equals 0 and the expansion around tau equal infinity are different. So there are some differences which make it more difficult to completely collapse one thing into the other. But my dream would have been to have at least a three-dimensional field theory associated to any toric-Calabi-Yau manifold, which would be different from the story you are mentioning, because the story you are mentioning is a story which involves compact Chern-Simons theory, and this is non-compact Chern-Simons theory. But we haven't been able to really to actually make this story to actually find it out. I mean, right now we are just at the level of formal similarities, not at good physical reasons or mathematical reasons for these similarities, unfortunately.
So thank you. There is a question by Jan Soiberman.
Yeah, hi. So actually, it's a bit related to the question asked by Vivek. In your topological string story, do you have some kind of difference equation, like quantized spectral curve? Which,
I mean, this is the
all right, good. Then okay. Then why you cannot proceed similarly to the beginning of your talk when you mentioned this Gayoto-Murnetsky, when you have geometric, you count as BPS curves and so on, so on.
Oh yeah. In principle, In principle, we could do that. Yeah, I mean, this is a question that could be asked. Now you do a kind of WKB analysis of this difference equation. Maybe you will find these integers or something related. Yeah, no, that could be done, but it's still not clear to me that this is going to give you the same invariants.
Okay, so that's a conjecture. And if you have
I haven't done any calculation, so I don't.
But if you have these integers, then you indeed can proceed and formulate the Riemann-Hilbert problem just by general.
Absolutely,
machinery.
That would be another direction, which I think is also very interesting, but I think it's slightly different from this one. But that would be another direction. So you take this WKB, you take this WKB curve that you can actually write down because you have an operator, so you have a Schrödinger equation associated to it, and then you try to do you try to understand now this WKB theory will have additional singularities because the variables are exponentiated. Again, this is this multi-covering story, and then you should be able to extract from this WKB theory everything you want, all this, and trans series, Stokes constants, and so on. That's another story that could be done, but it's slightly different. I mean, it's different from what I'm doing here.
Yeah, that's I noticed, but I thought that it's kind of was done because it's very natural.
Yeah, but it's not so easy because essentially working out the WKB theory of these difference operators is slightly more difficult precisely because of this additional multi-covering structure that you have. So I would expect to have a more complicated theory than a standard WKB of the Schrödinger equation.
Okay, thank you.
Right. There is another question by Jorgen.
Yeah, Marcus, I just wanted to ask you about the volume conjecture. So we have it right there on the screen now.
Yeah. This one.
Yeah. So, there is this. So of course, Renat's volume conjectured that he's invariant. The Kazhaev invariant grows with the volume. And then Renat and I somehow made this, state integral invariant. And the funny thing that we kind of observed with that was that, yes, we also believe that there is a volume conjecture. We made a volume conjecture for that, but that has exactly this minus sign that we see there.
Yes.
And it's kind of therefore very special in Chern-Simons theory because it's the smallest decay possible.
Yes.
And is there a similar significance or role of this in over on the toric side, toric Calabi-Yau somehow?
I mean, I think it's actually a very non-trivial conjecture from the point of view of quantum mechanics, because you are saying that you are taking a limit in which h bar goes to infinity but maybe that's actually why it's natural. I mean, you are taking a trace class operator, and then you are taking the limiting which h bar goes to infinity, and then, you know, this is exponentially decreasing. So that looks like natural, right? But I don't see a direct connection to what you have done. I mean, again, you know, if you work out the details, you can see that this trace is given by an integral, which looks very similar to your integral, and so on. So it's natural that it decreases like this. What is surprising from my point of view is that something that is obtained by quantizing the mirror curve, which in principle is an operator, right? You know, this operator here, that the asymptotics of the trace of this operator knows about a classical property of the Calabi-Yau, which is the volume at the conical point, essentially. So that's why I think it's very similar in spirit to Rinat's conjecture, but I don't have any deep interpretation about the plus or minus sign. I think it's natural here to have a decreasing exponential, but I don't have like any clear relationship to the inversion of sign that you noticed.
Yeah, I mean, Renat and I were sort of hoping that this will, you know, be a route to the other volume conjecture, of course. And so, for example, is there another point where it's exponentially increasing?
Yeah.
In the Calabi-Yau world.
That would be interesting to understand. Yeah.
Okay, thanks.
So thank you, Marcos. If there is no other question, first we should thank Marcos. I don't know, can just I will clap hands, but I think you can do that on the conversation.
Oh, Rinat is asking a question, I think.
Yeah. Yeah. So Rinat, do you have a question?
No, actually, it is not question. I was trying to clap.
Yeah, okay. Okay, so thanks a lot to Marcos to this good talk. I think that it is recorded, and you can the record will be put on the website. I hope this worked.
Yes, and I hope also
the slides too.
Yes, we will try. If Marcos, if you send those to Yanis, he will put them on the webpage.
Yeah, I'm going to do that.
Yeah.
Well, thanks a lot. Thanks a lot for the invitation and the opportunity to talk here, and thanks for the amazing environment of ReNewQuantum, which actually inspired me to do this work. It would have been impossible without all the brainstorming around ReNewQuantum.
Yeah. And when is the next seminar? I don't remember. Do you know?
So it's in a month's time, roughly. Yeah, I will talk about resurgence of now closed three manifolds as opposed to knots for WRT quantum invariants.
Okay, so thanks to everyone, and see you in 1 month.
Okay, thank you.
Okay, bye.